Hello, I am Neeraj. So today I will discuss on RoFormer. This is another paper which claims that when you use the large language model and train it for lower length sequences, then at a test time you can use it for higher length sequences. And like earlier paper that I discussed in previous video, it also attacks on the positional encoding part of the transformer, because it also claims that the transformer's vanilla version, which uses the positional encoding based on the sine and cosine functions, has some limitations, and due to those limitations it suffers a lot of problem. And due to those limitations, it has limitations. It limits the capacity of extrapolations of such kind of old vanilla models. So let us see that how it works and how we can use it. So let us first start with the vanilla transformer. So vanilla transformer, what we generally do, suppose we have a 4-word sentence like hello, how are you. So for that, when we pass these two like vanilla transformer, what we do, we just calculate the embedding. We add the embedding vector and we use this embedding vector and add a positional embedding vector with this. Now to compute the positional embedding vector, we generally use the sine and cosine function. So suppose we have embedding dimension 2, so d equal to 2. So in that case, suppose for first position we calculate the embedding, we got like 0.0 and 1.0. For first position we will use sine, and for this position we will use cos, and then we got this value. Similarly for position 1, if we pass this at I is equal to 0 here, we will get 0.088 value. If we provide I equal to 1 value to this, because this is odd, so we will use the cos function, so we will get the value 0.61. Similarly for position 3, for even embedding position, we use sine, and when we put the value of I equal to 0 and position equal to 2, and our embedding dimension is suppose embedding model dimension is 2. So based on that we will get some value like 0.49, and similarly for I is equal to 1 we will get 0.04. Now if we increase the position like 0, 1, 2, 3, 4, 5, 6, and for each of the embedding dimension we will get the following sine and cos values. So if you see those sine and cos values, then you will analyze that even if we increase the value, means its differences are not so high. For example, see here and here, and similarly you can see here and here, the differences are not much higher. Means and due to that, what happens when we try to just map like this, rotation map like this for every time. Suppose first time we say that word hello is coming, we got some value like some angle theta 1. Next time it come, maybe it will go here like that, and say that maybe it will go very much near to there and say that this is theta 2. Sometimes it may go there like theta 3. So you may not get like some continuity or some proportionalism kind of thing when we use such kind of periodic functions, sine and cosine based positional embeddings. So it actually affects the computation. So in that case, it also, due to this, it also limits the capacity of extrapolation or generalizability of the model after training. So this paper, RoFormer, actually proposed rotary positional embedding. So in the rotary positional embedding, what happens? So this paper proposed that instead of adding embedding plus positional embedding to the sequence and passing it as a query and key to the attention block of the transformer, we apply some rotatory positional embedding. Instead of that, just sine and cosine based positional embedding. So what it do? So what it does? So suppose we have words, sentences like hello, how are you? We have embedding dimension 2. So in that case, it takes the value of query and key. And suppose query and key values are there and its position is m, represented as m. So its index position is 1, index position 2, 3, 4 like that. So we take this index position and based on query, key, index position and the value of theta, that is represented as theta is equal to 10,000 to the power of minus 2i by d. That is taken from the that old vanilla transformer paper. Attention, all you need. So I have given all the citations, so you can see from there. Now based on that, it applies some Euler-like formula matrix and then multiply it with query key matrix. And based on that, it gets some rotation, means it rotates the query and q through some angle m theta 1. And then it passes that rotated, means the new positional embedding, positional encoding that is different from this, means a rotatory kind of positional encoding that is added with query and key, that it passes here. And we use this query and key, with the embedding having some rotatory embedding system with to the attention block architecture. So what happens in this case? So in this case, what happens? Suppose you have some word like hello. Suppose it comes at first time. We got we got some m theta 1 rotation. Now second time it will get, suppose we will get side m theta 2 rotation, m theta 3 rotation. We will get some meaningful kind of distances between each occurrences. Similarly, some word, suppose u is far from hello. So in that case, its rotation angle will be higher than rotation angle between like hello and how and some other words. So words which are far apart, the rotation angle will be higher. So due to this, if two words are come in the close context, the rotation angle will be arranged in such a way that we will get the higher dot product between query and key, means a higher similarity between query and key, because this dot product is nothing but cosine similarity between query and key. So to understand all those things like how cosine similarity and other things are working, you can see my part 1 of this video tutorial. Then you will easily understand that how we use such kind of query and key and its embedding in the next layer for transformer architecture and what is its importance. So this is the main funda, like how every time the rotation changes. So how rotation changes with those positions and the value of theta. So this is just for 2 dimensions. The paper also describes that how we can do or achieve the same thing for the higher dimensions. So here it is possible. In the board I have just explored the 2-dimensional cases. It is possible to go for multi-dimensional cases also. Suppose your sequences are very high, dimensions are very high, then in that case it is shown that with the diagonal we can take this expand this matrix and it can easily calculate. And another thing that I can show you, that the entire computation is not so tough to go through. So here you can see that the computationally rotatory, computationally it is highly computationally efficient, because it is just a task of matrix multiplications that you can see here. the entire computation is a matrix multiplications, like you are rotating it through m theta, theta 1, theta 2, m theta dy2, and here you can see the values. So, and another thing that has shown that in this figure, that if two words are very much close, far, means two words are very much far, then it may show that some very huge means gap in their actual values. So if the relative distances are too high, so you can see that, so relative upper bounds are also decreases. Now you can easily understand that the entire system is too easy to understand. Instead, if you just go through the mathematical part, and if you go through the one by one steps, it is very easy to prove that paper, like how it is working and how it is mathematically justifiable. But as an implementation part, it is also too easy to understand. And I will try to come up with some more tricks and algorithms that you can apply with your large language models to work with longer sequences and train it for low length sequences, and a lot of other features I will try to cover. So thanks for watching.